A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear students, today we are going to discuss synthesis of polyurethanes. The key concepts which will be discussed in this lecture will be introduction of polyurethanes. Then will be the manufacture of polyurethanes. There are three parts for the manufacture of polyurethanes: production of isocyanates, production of polyols, and C part is the production of polyurethanes. Then will be the manufacturing process that will be discussed. Polyurethane, PUR and PU. Polyurethane is a polymer composed of organic units joined by carbamate urethane links. What are carbamate links or urethane links? Here you can see the formula given above in pink color is the chemical structure of carbamate link, urethane linkage. What is that? That is actually carbamate is formed when proton of carbamic acid is replaced by a salt or something else. What is carbamic acid? Carbamic acid is an acid which is having a carboxylic group attached with an NH2 amino group. So here you can see in the compound, the formula given above of the urethane linkage is having a carboxyl group which is extended in the n number of same units is showing that there are extended units, n number of units, so same type, and this carboxyl group C double bond O is attached with NH, and then this N is attached with R, and so far. So carbamic acid is a carboxylic group which is attached with the carboxylic, the carbon of the carboxylic is attached with the nitrogen and a nitrogen of amine. So polyurethanes are the polymers which are containing carbamate or urethane linkage. So while most polyurethanes are thermosetting polymers, they do not melt when heated. Thermoplastic polyurethanes are also available. So you have studied the difference of thermoplastic and thermoset. Just for the sake of your review, thermoplastics are those which are easily molded in desired shape upon heating. They are linear or branched in structures, PVC, PE. But thermosets are those which resist deformation and solution once their final morphology is achieved. And how is that achieved? By cross-linking, by cutting. They cannot be remolded. They are hard, they are infeasible. Once they are heated, then they are hard and they cannot be molded again. They are having a cross-link structure. So thermosetting polymers, most polyurethanes are thermosetting polymers, but thermoplastic polyurethanes are also available. So thermosetting plastics are those which are easily molded in desirable shape upon heating. Mostly they are thermosetting polymers, but thermoplastic polyurethanes are also available. So Now, the polymeric materials known as polyurethanes form a family of polymers which are essentially different from most other plastics in that there is no urethane monomer. Like the name shows it is polyurethane, but there is no urethane monomer over here. But there is just a urethane linkage. And this polymer is invariably created during the manufacture of a particular object. When we are manufacturing a particular object, then this polymer is created. Its name shows it's a polyurethane, but it does not contain the monomer, urethane monomer. So other polymers, you see that ethylene, polyethylene, it is having ethylene monomer, and similar to that polyvinyl chloride, it is having vinyl chloride monomer, but this does not have a urethane monomer. The polyurethanes are made by the exothermic reactions between alcohols with two or more reactive hydroxyl groups per molecules, like diols, triols, polyols. So which kind of alcohols are reacting? The alcohols which are having hydroxyl groups but two or more reactive hydroxyl groups, like diols, triols, polyols. And isocyanates, isocyanate is a functionality which is having cyanide, like cyanide is having carbon to nitrogen triple bond, but isocyanate is having carbon to nitrogen double bond, and this carbon is further attached with an oxygen. So the carbon is attached with making its 4 bonds, but carbon is in the center, then it is attached with oxygen double bond, then it is attached with the nitrogen double bond, and this nitrogen further attached with the, like you can see NCO written. This is isocyanate group. So alcohols, diols, triols or polyols, when they react with isocyanates, those isocyanates which are having more than one reactive isocyanate group per molecule. So when both of these alcohols having 2 or more reactive hydroxyl groups per molecule, isocyanates, those are having more than one reactive isocyanate groups per molecules, diisocyanate or polyisocyanates, when they react exothermically, then polyurethanes are formed. And when they react, there is an exothermic reaction. Now, for example, here in the reaction given below, a diisocyanate is reacting with a diol. There is a diisocyanate shown on the left hand side, and diol is shown on the right hand side. The reactant on the left hand side is diisocyanate. It is having 2 isocyanate groups, and diol is having 2 hydroxyl groups, and any carbon chain is in between these. So when both of them are reacting, now you can again see carbamate linkage is shown in the pink color. So carbamate linkage is established, and the polyurethane and number of this repeating unit has been joined together to form this polyurethane. The group formed by the reaction between the 2 molecules is known as the urethane linkage. If there are only 2 molecules and they are joined together, like one isocyanate and one diisocyanate and one diol, this linkage which is in the pink color, that is shown as a urethane linkage. But when there will be n number of molecules reacting and n number of urethane linkages will be formed, then we shall say that this is polyurethane molecule. But now this urethane linkage is an essential part of the polyurethane molecule. Since polyurethanes contain 2 types of monomers which comprise one after the which polymerize one after the other. Like first you can see there in the product, first there is isocyanate group, then there is a diol group. Like you can see the isocyanate group, carbonyl, NH, R1, NH, carbonyl, oxygen, then this one oxygen is of the alcohol, then R2 and then O. They are polymerizing one after the other, so they are classified as alternating copolymers. So you have studied the types of the polymers, and you have studied the types of the polymers according to the arrangement of the monomers. So if the monomers are of different type and they are arranged one after the other, then that is a type of alternating copolymer. So both the isocyanates and polyols used to make the polyurethane contain on average 2 or more functional groups per molecule. Now just as for the introduction, where polyurethanes are used. So polyurethanes are used in the manufacture of high resilience foam seating. हाई रेजिलियंस मीन्स जिसमें ज़्यादा कुशनिंग होती है. रिजिड फोम इंसुलेशन पैनल्स, ऐसा फोम जिसमें रिजिडिटी होती है, इंसुलेशन के लिए भी जो यूज़ होता है. इंसुलेशन हीट ट्रांसफ़र को रोकने के लिए यूज़ होता है, ठंडी चीज़ को ठंडा रखने के लिए, इंसुलेट करने के लिए, और बाहर की हीट को अंदर आने से बचाने के लिए. माइक्रोसेल्युलर फोम सील्स. Microcellular foam seals, these are the seals which help, which are present in the devices and have to join the systems or mechanisms together by preventing leakage in like a pumping system, or so they exclude contaminations. They just seal the system. So they in gaskets, the microcellular foam seals, they are used in the like the formation of gaskets. What are the gaskets? Gaskets are, it is a type of mechanical seal which is filling the space between two or more mating surfaces, so that prevents the leakage from or into the joined object while under compression. When, like you can say that this gasket is a type of seal when two surfaces are mating with each other, so it prevents the linkage when the two objects, while they are under compression, they are very close to each other, and compression is happening in between them. So they are also used to make spray foam. Spray foam, you know what is the spray foam? Is a material that is react when it is mixed with each other. They expand 30 to 60 times its liquid volume after it is sprayed in a place. यानी आप उसको जब स्प्रे कर देते हैं तो उसका वॉल्यूम 30 to 60 टाइम्स अपने ओरिजिनल वॉल्यूम से बढ़ जाता है, एक्सपैंड हो जाता है. तो ये बहुत सी जगहों पर जो है ये यूज़ होता है पैकिंग मटेरियल वगैरह के तौर पे, स्प्रे फोम. सो इट इज़ ऑल्सो यूज्ड फॉर मेकिंग ड्यूरेबल इलास्टोमेरिक व्हील्स, टायर्स, लाइक रोलर कोस्टर्स जो होती हैं, एक्सेलरेटर्स होते हैं, शॉपिंग कार्ट्स होते हैं, एलिवेटर होता है, स्केट बोर्ड्स होते हैं, स्केट बोर्ड्स जो जिससे स्केटिंग करते हैं, व्हील्स, ऑटोमोटिव सस्पेंशन, बुशिंग्स, मशीन्स के अंदर जो बुशिंग्स होती हैं जो हेल्प करती हैं पहिए के चलने में, व्हील्स वगैरह में, इलेक्ट्रिकल पॉटिंग कंपाउंड्स, हाई परफॉर्मेंस एडहेसिव्स, surface coating and sealants, synthetic fibers, for example spandex, carpet, underlay, hard plastic parts, electronic instruments, etc. So There are too many uses of polyurethanes. This is just a brief introduction, so we shall carry the manufacture senses of polyurethanes, and then we shall go towards applications. There will be a separate lecture, but here just for the introduction, for the sake of introduction of polyurethanes, these uses or these applications of polyurethanes are briefly described here. And now we shall study the manufacture of polyurethanes. As polyurethanes are made from the reaction between an isocyanate and a polyol. So this section is divided into three parts. Production of isocyanates, then will be discussed production of polyols, then will be discussed production of polyurethanes. So the first one part is the production of isocyanates. Although many aromatic and aliphatic polyisocyanates exist, they already exist, many aromatic and aliphatic polyisocyanates, two are of particular industrial importance. Each of them has variants, and together they form the basis of about 95% of all polyurethanes. So, which two are particularly of industrial importance? TDI, MDI. What is TDI? TDI is toluene diisocyanate. There is a diisocyanate, but that is attached with a toluene, or it is also called methylbenzene diisocyanate. This is TDI, diisocyanate, but it is attached with the toluene, so it is called TDI. MDI, that is methylene diphenyl diisocyanate. Both of them are diisocyanate because we have studied that isocyanate molecule should be having at least two functionalities, isocyanate functionalities per molecule. So diisocyanate is over here of particular importance. When toluene diisocyanate, then it is TDI, and when methylene diphenyl diisocyanate, then it is MDI. The other name of this MDI is diphenyl methane diisocyanate. So structures we shall be going through on the next slides. So we have seen that for the manufacture of polyurethanes we need three steps. We can divide the production of polyurethanes into three parts: production of isocyanates, production of polyols, and production of polyurethanes. Part 1 or A part, the production of isocyanates. So there are many aliphatic or aromatic isocyanates exist, but two are of particular industrial importance. These make up about 95% of all polyurethanes. So they and their variants, TDI and MDI. Now here you can see TDI. Two isomers are shown over here. So TDI was developed first, but is now used mainly in the production of low density flexible foams for cushions. So the mixture of diisocyanates known as TDI consists of two isomers. You can see the isomer on the left hand side is the isomer having diisocyanate functional groups at 2 and 4 position of the toluene, and on the diisocyanate, which is at the right hand side, is having isocyanate functionality on 2 and 6 position. So these are TDI is in the form of these two isomers, and that is used for the production of low density flexible foams that are made up for cushions. मिथाइल बेंजीन डाइआइसोसायनेट, दो आइसोमर्स होते हैं इसके मिथाइल बेंजीन डाइआइसोसायनेट के. So the starting material is methyl benzene, that is called toluene. So when it reacts with mixed acid, nitric acid and sulfuric acid, the two isomers of nitromethylbenzene are the main products. So how is the preparation of isocyanate is initiated? That is initiated by the nitration of methylbenzene, or you can say that nitration of toluene. The nitration of toluene with the help of two acids mixed together, nitric acid and sulfuric acid, two isomers of nitromethylbenzene, NMB, are the main products. One isomer is 2-nitromethylbenzene and the other isomer is 4-nitromethylbenzene. So the first reaction is the nitration of toluene, giving two isomers in the product, 2-nitromethylbenzene and 4-nitromethylbenzene. If this mixture is nitrated further, what will be? After the mononitration, dinitromethylbenzene will be produced. In industry, they are known by their trivial names: 2,4-dinitrotoluene and 2,6-dinitrotoluene, DNT. 80% is 2,4-dinitrotoluene and 20% is 2,6-dinitrotoluene. So both of these are produced if the mixture is nitrated further. So one more nitro group will be attached. First there was nitro at ortho or para position. So at ortho position or the para position, the nitration was done in the first step. If we keep on doing further nitration, then dinitro product will be formed. So the dinitro product will be 2,4-dinitrotoluene or 2,6-dinitrotoluene. 2,6-dinitrotoluene is in only in lower percentage. It is only 20%, while 2,4-dinitrotoluene is 80%. The reason may be the steric hindrance, which is not letting the 2,6-dinitrotoluene in more percentage, because the nitro which is away from methyl is more stable. So 2,4-dinitrotoluene is in the percentage of 2,4-dinitrotoluene is greater than 2,6-dinitrotoluene. Mixture of these nitrobenzenes is then reduced to the corresponding amines. So just by reduction, the NO2 group is converted into NH2. In turn, the amines known commercially as toluene diamines, TDA, they are heated with carbonyl chloride, phosgene. Carbonyl chloride, carbonyl with attached with two chloride on both sides, that is called phosgene. So TDA, toluene diamines, when are heated with phosgene, they also produce diisocyanates, and this process can be carried out in the liquid phase with chlorobenzene as a solvent at about 350 Kelvin. So one method was that mononitration, then dinitration, then reduction of these dinitrobenzenes. Otherwise commercially, toluene diamines are heated with phosgene or carbonyl chloride to produce diisocyanates. So this is done in the presence of chlorobenzene as a solvent. So the reaction is carried out in liquid phase at about 350 kelvins. So here is the reaction of diamine, the reaction of toluene diamine with phosgene, the carbonyl chloride. You can see 2 moles of carbonyl chloride phosgene gas are reacting with toluene diamine, and they are producing isocyanate. How isocyanate is produced? Before the generation of isocyanate, you can see in the first reaction there is an amide is generated first, and then you can say an acid halide on one side of the carbonyl group there is NH, and on the other side there is chloro. So this can be acid halide. So actually this is carbonyl and NH carbamate linkage. So this further will react with HCl to produce cyanate. So each one of the functionality on the product of phosgene and toluene diamine will be converted into isocyanate functionality. So both of the ortho and para substituents will be converted into isocyanate functionalities by reaction of the product of the first step with HCl. So this reaction of diamine with carbonyl chloride is actually vaporizing the diamine at 600 Kelvin with carbonyl chloride in the gaseous phase can also be done. Alternatively, first we have discussed the reaction of diamine with carbonyl chloride in liquid phase in the presence of solvent. Now we can vaporize the diamine, and then we can mix both of the gaseous reactants, you can say that. So carbonyl chloride then can react with the vaporized diamine. So this is an environmental and economic improvement over the liquid phase process, as no solvent is needed. So if we are using the gaseous phase of the reaction, we do not need a solvent for this reaction. So in either process, the reagent is the isomeric mixture of dinitro compounds. So 80% 2,4 and 20% 2,6 will be the product, and it is a mixture of diisocyanates in the same proportions. If we are using either we are using the dinitro compounds 80% 2,4 and 20% 2,6 dinitro compound, and the isomeric mixture of dinitro compounds, or we are using the other one strategy. In both the cases, the product is a mixture of the diisocyanates, and the proportion even is the same in both of the processes. So it is expensive to produce this mixture in different proportions. It means purifying the mixture of the nitromethyl benzenes NMB by a very careful distillation. Now what is going on? If we want to change the proportion, if you want to produce this mixture not in 80 and 20% proportion, but if we want to make this mixture in somewhat else proportion, we shall have to purify the mixture. Both of the isomers, we shall have to do a very careful distillation of nitromethyl benzenes, and then we shall get them separated, and then we shall use one of them in a greater percentage to be converted into the product. But this is an energy consuming process, this is expensive process. So most of the times the expensive processes are not economical, so they are not industrially applied. So what have we seen? That we can do two processes. Either we can convert, either we can do the nitration of the toluene, then we can do the dinitration, then we can do the reduction of the dinitrobenzene, a mixture of dinitrobenzenes, mixture of two isomers, and then we can convert that amine into the, by reaction of that amine with phosgene to convert into the isocyanate. Or we can do what? We can do the commercially available diamine, toluene diamine, and we can react that with the phosgene, and we can do these into any of the phase. Like gaseous phase, we can do the reaction of diamine with the carbonyl chloride, or we can do this reaction in the liquid phase. So in both the cases, the proportion of the diisocyanates mixture is the same, and to get any other proportion of the mixtures other than 80 to 20% ratio of 2,4 and 2,6 isomers, that will be a very expensive process because it will need distillation. It is more fruitful to produce different properties in the polyurethanes by using different polyols which react with the 80-20 mixture of TDI to produce the polymers. If any industrialist or any industry is using different type of polyols to react with the diisocyanate, toluene diisocyanate, which is in the form of 80 to 20 ratio mixture. There will be different type of polyurethanes will be produced, and they will be having different properties. So when they are having different properties, so they will be more fruitful, they will be used in a versatile manner in different places and different scenarios. So MDI is more complex. the term MDI refers to the mixture of the three isomers as shown in the figure below. They like one is 2,4 MDI methylene diisocyanate, and then is 2 prime. The prime is showing 1, 2 is showing one major ring, and 2 prime is showing the other ring. One ring we shall represent by a simple number, and the other ring we shall represent by prime. So 2,4 prime MDI means one isocyanate is present on one phenyl ring and the 2 position of one phenyl ring, as you are looking at the above structure, the first one structure. And 4 prime shows that at the para position of the second phenyl ring. So you are looking that where there is methylene CH2, the other isocyanate is just para position to that methylene. So that is 4 prime. So 2 prime MDI means one isocyanate is at 2 position of one phenyl ring, and the other isocyanate is present at the 2 position from the methylene of the other methylene, 2 position from methylene, and the third isomer is 4 prime, that is both isocyanates are present at para position from the methylene linkage. Now numbering of position or naming for naming isomers of methylene diphenyl diisocyanate is like that. As you are looking at the very right hand side, there is a figure in which the numbering is there. Very next to the methylene, the carbon which is directly linked to the methylene is 1, and the very next to the methylene is 2, then 3, and then 4. Similarly, one phenyl ring is labeled as 1, 2, 3, 4, and the other one phenyl ring is labeled as 1 prime, 2 prime, 3 prime, and 4 prime. Now you can recheck the numbering of the isocyanate groups again: 2, 4 prime MDI, 2 prime MDI, and 4 prime MDI. Second part in the synthesis of in the production of polyurethanes is part B, is production of polyols. Polyols are either hydroxyl terminated polyethers. About 90% of the total polyurethane manufacturers which are used are hydroxyl terminated polyethers, or they can be hydroxyl terminated polyesters. So they can be hydroxyl terminated polyethers or hydroxyl terminated polyesters. So they have been developed to have the necessary reactivity with the isocyanate that will be used and to produce polyurethanes with specific properties. So isocyanates have been developed for the necessary reactivity, and they will be used to produce polyurethanes, and they will react with isocyanate and will make polyurethanes. Each polyol will be giving a different properties to the polyurethanes. So an example of a polyol with 2 hydroxyl groups is a long chain diol, is one which is made from epoxy propane, and like epoxy propane, that is propylene oxide by the interaction of propane with 1,2-diol, which itself is formed from epoxy propane by hydrolysis. So An example of polyol with two hydroxyl groups is one that is made from epoxy propane. An example of a polyol which contains three hydroxyl group is produced from propane 1,2,3-triol, glycerol and epoxy propane. So when epoxy propane and propane 1,2,3-triol, the glycerol is propane 1,2,3-triol. When these two make a polyol. These two together make a polyol which is having three hydroxyl groups. So on the next slide you shall just see how this 1,2,3-triol, propane 1,2,3-triol, glycerol and epoxy propane, propylene oxide, which is epoxy propane, which is formed by the interaction of propane 1,2-diol. Propane 1,2-diol is actually coming from the hydrolysis of epoxy propane. So epoxy propane, when epoxy propane and glycerol are reacting together, they are making up a polyol. That polyol is containing three hydroxyl groups. So you can see that type of polyol on the next slide. So here you can see propane 1,2,3-triol at the very left side of the reactants, and epoxy propane, which is after the glycerol, in which there are three carbons colored pink. Three carbons are colored pink in this epoxy propane. So when both of these are making up a polyol, and this polyol is containing three hydroxyl groups. Actually, glycerol, when combines with this epoxy propane, that is giving three carbons and one oxygen just after the glycerol oxygens, and the epoxy propane is also giving two hydroxypropyl chain also, which is attached with that portion which is in the bracket and is pink colored. So the above polymer products may be represented as this idealized structure. So here the structure which is shown down, the carbons are shown in the form of chains. Soybean oil contains triglycerides. They are made up of long chain triglycerides are made up of long chain saturated and unsaturated carboxylic acids. So soybean is containing these triglycerides, which are actually made up of long chains of unsaturated and saturated carboxylic acids. After dehydrogenation, they can on reaction with epoxy propane, these triglycerides which are present in soybean oil, they form a mixture of polyols, and those polyols are suitable for the manufacture of wide range of polyurethanes. The triglycerides which are present in the soybean oil, when we do hydrogenation to those triglycerides, triglycerides of long chain unsaturated and saturated carboxylic acid, we just first do hydrogenation and then we shall do the reaction with epoxy propane. So a mixture of polyols will be produced that will be suitable to manufacture a wide range of polyurethanes. So these biopols these are biopoles, mean the use of these biopoles means that at least part of the polymer is derived from renewable sources. Renewable sources means something which is coming from the living organisms or plants or animals. So with the reference to that, we are calling them biopoles. Okay, now the P part of our production is the production of polyurethanes. If the polyol has 2 hydroxyl group and this is mixed with either TDI, toluene diisocyanate, or MDI, methylene diphenyl diisocyanate, it can be mixed with any one of these, TDI or MDI. So the polyol which is having 2 hydroxyl groups, if it is mixed with TDI or MDI, a linear polymer is produced. For example, a linear polyurethane is produced by the reaction with a diisocyanate and the simplest diol, that is ethane 1,2-diol. So condensation polymerization occurs here. In the condensation polymerization, what happens? Small molecules are removed during the condensation of the 2 reactants. So what are we going to do for making up polyurethanes? We are reacting the polyols with diisocyanates. This polyol having 2 hydroxyl groups, ethane 1,2-diol, is being treated with diisocyanate to produce polyurethane. So you can check the structure on the next slide. Now here you can see 4,4' MDI. The isocyanate group are present at the 4 positions on both phenyl rings. 1 phenyl ring 4 and 4' for the other isocyanate which is present on the other phenyl ring. So 4,4' MDI is when reacting with ethane 1,2-diol. A urethane linkage is being produced. You can see that the urethane linkage is colored pink here. So this is a polyurethane. The diphenyl and methylene diphenyl is from the 4,4' MDI, and the linkage is from the NHCO from MDI and CH2O from the diol. So this is a polyurethane in this by this reaction is produced. Now if we check the reaction with 2,6-TDI, toluene diisocyanate, so that is a mixture of actually 2,4 and 2,6 isomers, and we just treat it with a polyol of low relative molecular mass and is very small. So this is 1-methyl, but this is the monomer is CH3CH2OH, but N is over here. It does mean this can be a single one CH3CH2 unit or CH3CH2CH3CHCH2O. One this unit can be once over there or twice or thrice, but very low relative mass, a polyol of very low relative mass will be like N will be very small over here. So when this polyol is reacting with TDI, we are getting the first step in which urethane linkage is formed, and carbamate or urethane linkage is formed, and then in the subsequent steps, this first the dimer is produced from the two monomers, and then afterwards in the subsequent steps more monomers are being attached with this chain, and the chain becomes longer and longer. So a long chain linear polyol is produced over here. So this is a long chain linear polyol, means N is here showing that now it is a polymer, so there will be so many numbers of this CH3CH2 CH2O units. So now N will be N is that one which is coming from the reactant. N is the same, but the structure will be repeated like M. Here you can see the M is showing the number of repeating units. So again and again the same will be joining together, and there will be making a polymer. If polyol is having more than 2 reactive hydroxyl groups, so the adjacent long chain molecule becomes linked at intermediate point. So if there are more than 2 reactive hydroxyl groups, so any one of the adjacent long chain molecule will be linked at the intermediate points. So this will be creating a cross-linking. A stiffer polymer structure will be produced, and mechanical characteristics of that polymer will be improved, and which will be exploited in the development of rigid polyurethanes, the cross-linking. If more than 2 reactive hydroxyl groups are present, they become linked with the long chain molecules at intermediate points. So the diisocyanates such as MDI or TDI, when reacts with a polyol with 3 hydroxyl groups, such as which was derived from propane 1,2,3-triol glycerol and epoxy ethane, that polyol was having 3 hydroxyl groups. So they will undergo cross-linking to form a rigid thermosetting polymer. So a thermosetting or rigid polymer will be produced. As well as polyisocyanate and polyols. For the manufacture of polyurethanes, a variety of other chemicals are also needed to control polyurethane forming reactions and to create exactly the right products in the end. The right properties in the end product. Some other chemicals are also necessary. So all these practical polyurethane systems include some, but not necessary all of these, which are described in table 1 on the next slide. The additives which are used are catalysts to speed up the reaction between polyol and polyisocyanate. Cross-linking and chain extending agents are added to modify the structure of a polyurethane molecule and for provision of mechanical mechanical reinforcement, so that the physical properties will be improved. So adding polyisocyanate or polyol with more functional groups will increase the cross-linking, as we have seen that more than 2 hydroxyl groups are making cross-linking with the long carbon chains. Blowing agent surfactants. These are added to create polyurethane as a foam, and as a foam they control the bubble formation during the reaction, and hence the cell structure of the foam. So they just they just make the polyurethane as a foam. So the foaming controls the bubble formation actually, and the structure of the foam is controlled by the blowing agents or surfactants. Pigments are used to to create colored polyurethanes for their aesthetic reasons and for identification of the polyurethanes. Fillers are used to improve the properties such as stiffness and to reduce overall cost. Flame retardants are used to reduce the flammability of the end product. Smoke suppressants are used to reduce the rate at which the smoke is generated when the polyurethane is burnt. So they will suppress the smoke when polyurethanes are burnt. Smoke suppressants are also added. Plasticizers are added to reduce the hardness of the product. So this figure is showing that the broken limbs are encased in polyester bandage, and that is containing the linear polyurethane. So after bandage has been wound around the limb, it is soaked into the water, and by soaking into the water produces cross link between the polyurethane molecules, so producing a strong but light cast over the broken bone. Now manufacturing process. It is just like an example is that like when we manufacture a molded item that might otherwise be made from the thermoplastic polymer by injection molding. So it is just like the manufacture of molded item. Like what? For making up polyurethanes, we mix exactly the right masses of two major components, polyisocyanate and polyol, or which must be liquids. So the reaction starts immediately and give the solid polymer, and depending on the formulation, the catalyst used and the application, the reaction is typically completed in between few seconds to some minutes. So this is just like the manufacturing of a molded item. So it is essential to, at that time, it is essential to dispense the reacting liquid mixture into the mold, वो जो सांचा सा होता है जिसमें उसको हमने मोल्ड करना होता है, और क्लीन करना, combine mixing and dispensing equipment ready so that it should be ready for the next operation. So the exothermic chemical reaction is completed within the mold, and the manufactured article can be taken from the mold immediately. मोल्ड में डाला और वो फ़ौरन बन जाता है, और उसको एक्सोथर्मिक रिएक्शन हो हीट जो है दैट गोज़ आउट और वो फ़ौरन बन जाता है. Formed polyurethanes. When two liquids react, a solid polymer is formed. The polymer may be elastic or rigid. However, it may also contain bubbles of gas so that it's a cellular or foam. It is cellular. Sometimes when the two liquids react, a solid polymer is formed. That the polymer may be elastic or rigid. However, sometimes it contains bubbles of gas, so that it is cellular. It is a foam. So it may be a solid or maybe a foam. Now, if we want to produce foamed polyurethane, so there are two possible ways for generating gas inside the reacting liquid mixture. The so-called chemical blowing uses water that may have been added to the polyol, which reacts with some of the polyisocyanate to create carbon dioxide. So here's a reaction given. The diisocyanate reacts with water and produces carbon dioxide, and that carbon dioxide produces foaming or bubbling over there. So due to that bubbling, the gas is generated over there, and that blows up. The formed polyurethane is produced. Alternatively, physical blowing, a liquid with a low boiling point, for example pentane, is mixed into the polyol. This reaction is exothermic, and so as it proceeds, the mixture warms up and pentane vaporizes along with that. So the tiny amount of the air that is dispersed through the mixture of polyisocyanate and polyol. So this is providing the vaporization of the pentane due to exothermic reaction. This is providing nucleation seed for the multitude of gas bubbles that are produced throughout the polymer. So this will initiate the bubbling phenomena, bubbling procedure, gas bubbling. Heat makes the bubbles expand. There will be heat, the bubbles will expand, they will make bigger and bigger. So under the chemical reaction changes the liquid to solid polymer, and the valuable gas pressure cannot create any further expansion. That is expanded up to that extent. Beyond that extent it cannot be the expansion cannot be done, so it expands it to that much extent. A shoe sole, for example, may be blown to double the volume of the solid polymer. Like a shoe sole is blown and it makes up the double volume of the solid polymer, for example, and formed polymer. These are two things. So solid polymer is having lesser volume, and the blown or formed polymer is having double volume. This process is so versatile that expansion can be taken much further. So expansion can be taken by this process. Now the figure 2 is showing that during the manufacture, the chair's textile cover is filled with a mixture of the reactants and that which produce the polyurethane foam, and the chair is given its original shape by filling out the seat surface with foam as a full-size doll sits in its chair. So just blown the polymer and that foam is produced. So just the cover is put on the chair, and then the mixture of the reactants is introduced into that, and then which produce the polyurethane foam. So this is one example. Adhesion: in the final stage, the polyurethane forming reaction, the mixture becomes a gel with the very effective surface adhesion. Hence, polyurethanes can be used as adhesives also, because at the end of the reaction in the final stage, a gel is produced that is having very effective surface adhesion. Equally important is the fact that polyurethanes, which are being created as, for example, cushioning or insulation materials, can be bonded to the surface materials without the introduction of separate adhesives. So that gel is so having adhesive properties that without any separate adhesives, they can be cushioning or insulating materials can be bonded to the surface of the materials. So the flexible foam and fabric can create a composite cushion or rigid foam and sheet building materials. For example, plaster board, steel sheet, plywood can provide composite building insulation panels. So this foam can also flexible foam and flexible fabric can create a composite cushion or rigid foam and sheet building material which can provide composite building insulation panels. So if we want to make composite building insulation panels, so we can utilize polyurethane flexible foam or fabric.